Bismillahirrahmanirrahim. Today is our second lecture of the series of internal combustion engine. Today I will be talking about chapter 2, the operating characteristics of an engine. What are the operating characteristics? How we can judge an engine in a mathematical way. First, the engine parameters. Okay, now focus on your screen on the left side. You have a figure of this single cylinder engine with a piston and a connecting rod. This is a piston and cylinder geometry of a reciprocating engine. Here on the top, you have this B. This B is your bore, and as you know, the bore is the inner dia of the cylinder or the piston face dia. Okay. Now, then you have S, stroke. The movement of a piston from this BDC to TDC is known as your stroke, or from TDC to BDC. That length which the piston cover is known as stroke. Then R, the distance from the center of the gudgeon pin or the piston pin or the wrist pin to the crankshaft where the piston is attached is known as the length of a connecting rod, and it is denoted by R. A is the offset and at which from the center of the crankshaft at point which your connecting rod is attached to the crankshaft. Now this S, small s, this is different than this stroke S. Okay, this is the piston position at different location when we have different value of this crank angle theta. Okay, theta is changing from this 0 degree to 180 degree, and then from 180 degree to 360 degree. Theta values are changing, so this S will be changing the piston position in the cylinder or the combustion chamber. And as you know, the volume on the top of the piston, when piston is at your TDC, the volume is known as your clearance volume, and the volume VD, the pistons which cover from VDC to TDC, is known as your displacement volume. Okay. Now, for an engine with a bore B, as you have this crank offset A, the stroke length S turning at an engine speed of N, you can denote it with S is equal to 2N. So this your stroke is 2A, right? This is your A and this dia, okay? So stroke is equal to 2 into crank offset. Now the average piston speed UP bar is equal to 2 into strokes per revolution, then number of revolutions per minute in which the crankshaft is moving and the stroke length which is covering. Multiply by 2. So N is generally given in revolutions per minute. UP, the average piston speed, is generally in meters per second, or we can also denote in foot per second. And B is your bore, B, A is your crank offset, and S is your stroke. All they are in meter or centimeter or feet or in inches, whichever the system you are using. Now, from the calculation and experience, the average piston speed for all engine will normally be in the range of 5 to 15 meters per second or 15 to 50 feet per second. The average piston speed, the UP bar of an engine, is in the range of 5 to 15 meters per second, with large diesel engine on the lower end on this nearer to the 5, and high performance automobile engine on the high end nearer to the 15 side. Remember this range in your mind because we will be referring to this range when we will solving the example. So 5 to 15 meter per second is the average piston speed range. Now, engine parameters, why? There are two reasons why engine operating in this range. What are those two reasons? First, this is about the safe limit, which can be tolerated by the material strength of the engine component. So we have to play in a safe limit of the material. So that's why the speed range is 5 to 15. For each revolution of the engine, each piston is twice accelerated from top to maximum speed and back to stop. When your piston is at BDC and it's going to TDC, from zero, it is attaining a maximum speed, and TDC, it is again going to for a zero. So from zero, attaining maximum speed, from maximum speed to zero, and then again this same process. So you have to be in this safe limit. The second reason why maximum average piston speed is limited because of the gas flow into and out of the cylinder. So the volume coming in and the volume going out of the cylinder is the second reason to have this range. Piston speed determines the instantaneous flow rate of the air-fuel mixture into the cylinder during intake and exhaust flow out of the cylinder during the exhaust stroke. Higher piston speed would require larger valves. Which valves? Larger valves, intake valves, to allow for higher flow rates. In most engines, valves are at maximum size with no room of enlargement. When we will study the valves, their geometry and their sizes and dimension, we will study this aspect. So, higher the piston speed will require larger valves to allow for higher flow rates. Maybe it's intake and exhaust valve. In most engine, valves are at maximum size with no room of enlargement. So we have to keep that range 5 to 15 meters per second of an average piston speed. Now, engine's parameter, when you have bore and stroke of the same length, then the engine is called as square engine. Your bore dimensions and the stroke dimensions means the length or the dimensions are same, means if the bore is of 4 inches or 4 centimeter and stroke is of the same value, then the engine is square. And next position is under square engine. When your bore is less than your stroke, means the dimensions of the bore is less than your stroke value, then we call that under square engine, that engine. If next condition is over square engine, when your bore value is greater than your stroke value, your bore is having a 6 inches and your stroke is having only 2 inches. So then we call it as over square engine. We will be referring to these terms when we will solving the example and the problems. Now, the distance between the wrist pin axis and the crank axis. So that is defined by this equation. Remember this figure. S is equal to offset, crank offset A cos of theta plus R. R is the connecting rod length minus R square minus A square. A square is your crank offset and sine theta. Basically, simple formula to find out the distance of S piston distance at that given geometry. A is your crank offset, R is your connecting rod length, theta is the crank angle which is measured from the cylinder center and is zero when the piston is at TDC. When your theta, the piston is at this position, means at TDC, your theta is zero. So we will measure in this direction. So S is equal to A crank offset into cos theta plus under square R is your connecting rod length minus A square sine square theta. So you can find out the location of the piston at that point. Now the distance S between the crank axis and the distance wrist pin axis is given by this equation as we have already discussed. These are the same parameters. Now when S is differentiated with respect to time, now we differentiate this equation with respect to time. Then we get the instantaneous piston speed, UP. Then we get when the distance, as you know, the speed is differentiated with respect to time, then we will get the instantaneous piston speed. UP is equal to ds, derivative of that distance s divided by the time. So the ratio of the instantaneous piston speed divided by the average piston speed can be written as, so UP, the instantaneous piston speed divided by the average piston speed, is equal to pi by 2 sine theta bracket 1 plus bracket cos theta divided by under square r square. So no, this r is different. Minus sine square theta. What is this r? So this R is the ratio of the connecting rod length to crank offset and usually has a value of 3 to 4 for a small engine, increasing 5 to 10 for the largest engine. We will see the effects of R on the piston. So this R is different. This is the length of the connecting rod, and this R is the ratio of the connecting rod length to the crank offset, and usually has a value of 3 to 4 for small engine. Remember this ranges. We will be referring to these when we will be solving problem and examples. 3 to 4 for small engines, increasing 5 to 10 for the large engines. Okay, the displacement or the displacement volume VD is the volume displaced by the piston as it travels from BDC to TDC or from TDC to BDC. So the volume displacement volume is equal to volume at BDC minus volume at TDC. Now see the value theta degree R and instantaneous piston speed divided by the average piston speed. Let's see what the figure is. Instantaneous piston speed relative to average piston speed as a function of crank angle theta for various R values, where R is equal to the connecting rod length divided by crank offset. So when we have different on x-axis, we have a crank angle theta from 0 to 180 degree. On y-axis, we have a ratio of the instantaneous piston speed divided by the average piston speed from 0 to 1.8. Now, when you have a R is equal to 3, you have this curve. And if R is equal to 5 with this curve and R is equal to 10, this curve means angle changes and your instantaneous piston speed and average piston speed also changes. So these are the plotting curves when you have different value of R with respect to crank angle and the ratio of instantaneous piston speed with respect to the average piston speed. Now, some book called this swept volume. Displacement can be for one cylinder or for the entire engine. For one cylinder, remember, the displacement volume is pi by 4 d square into s, del d square into length. So here we are using bore and stroke. So the displacement volume of a cylinder will be pi by 4 bore square into stroke. Okay. Now for entire engine, when in engine you have a different number of cylinders, so NC, so different number of cylinder. If you have a 2-cylinder, 3-cylinder, 4-cylinder, that will be the displacement volume of the complete cylinder. So VD is equal to NC pi by 4 bore square into stroke. Most of my students do this mistake. When I give the example or the question, the volume of the engine is 3.6 liter. So it is the complete volume of the engine, 3.6 liter, not a single cylinder. So you have to cater for the number of cylinder which is inside the engine. The next point is volume of the engine is 3.6 liter. It has a 4 cylinder. So NC is 4. So you have to cater for the number of cylinder and the volume of the engine. So you have to very careful whether it is a 1 cylinder or a complete engine. So B is the bore, cylinder bore, S is stroke number of the engine cylinder. Now engine displacement can be given in number of units, meter cube, centimeter cube, inch cube, and most commonly in liters. As you have seen, 2.8 liter, 2 liters, or 2.5 liter, or 1.3 liter vehicles in your general life. Now, displacement or displacement volume, as we know, also known as the swept volume, VD, is the volume displaced by the piston as it travels from BDC to TDC. So the displacement volume is volume at BDC minus volume at TDC. As you know, when the piston is at TDC, the volume in the combustion chamber or the cylinder is the clearance volume at that time. Okay, so we can replace this thing. Volume at BDC is equal to clearance volume plus displacement volume. So total volume, displacement volume, or the swept volume is volume at BDC, and that volume at BDC is the combination of volume, clearance volume plus the displacement volume. Now, the compression ratio of an engine is defined. So this RC is different from your this R. Remember this thing. This R is the length of the connecting rod. Okay. And this RC is your compression ratio. So these two are different. The compression ratio is defined as volume at BDC divided by a volume at TDC. That is your compression ratio. Okay. So volume at BDC, total volume, divided by the volume at TDC, only the clearance volume. So that clearance volume, VC plus VD divided by VC, that is your compression ratio. In modern SI engine or spark ignition engine, we generally have a compression ratio of the range of 8 to 11. Okay. And in CI engine, the compression ignition engine, the ratio range is 12 to 24. Remember these ranges. Engine with supercharger or turbochargers usually have lower compression ratio than naturally aspirated engine. So engine with supercharger or turbocharger, these two are the devices. As we have studied in chapter 1, supercharger is placed on your intake manifold. It is used to increase the inflow, the volume of the air fuel mixture inside the combustion chamber or the cylinder. And turbocharger is used on the exhaust manifold. It used to extract the exhaust gases and create a vacuum to fill that vacuum, and fresh air has to be rushed in. So in both these are basically increasing the volumetric efficiency of the engine. To increase the volumetric efficiency of the engine, they are increasing the inflow and the outflow. And those engine having equipped with supercharger or turbocharger having a lower compression ratio as compared to the naturally aspirated engine in which you don't have these arrangement, these devices. Those are naturally aspirated engine. They have a higher compression ratio. Now, the cylinder volume V at any crank angle is V is equal to VC plus the area into that distance. So the volume, we want to find that volume at any crank angle theta. Theta may from TDC to BDC from 0 to 180 degree. We have to find that volume, the piston of is at what location, and the volume at that point will be what. So clearance volume plus the volume at that point. So bore into stroke, area into that stroke, pi by d square by 4 R is your connecting rod length, plus A is your crank offset minus that piston location at that instance. So that is your S. Now, this can also be written in non-dimensional form divided by volume, clearance volume, substituting for R, A, and S and employing the definition of R. We can put volume at that instant divided by the clearance volume is equal to 1 plus 1 by 2 RC. This is the compression ratio minus 1, bracket close, then bracket. This R is the ratio of, as we have ratio of the connecting rod to the crank offset plus 1 minus cos theta minus under square R square minus sine square theta, where VC is the clearance volume, B is your bore, R is the connecting rod, A is the crank offset, S is the piston position at that location. Okay, so we can write this volume equation in non-dimensional form like this. Now, where RC is the compression ratio, R is the ratio of the connecting rod length to the crank offset, the cross-sectional area of the cylinder and the surface area of the flat top piston are each given by AP is your the pi by 4 B square. The combustion chamber surface area is the area of the combustion chamber plus the cross-sectional area of the cylinder or surface area of the top piston AP plus pi B R plus A minus S, where ACH is the cylinder head surface area, which is somewhat larger than your AP piston A top flat area. Then if the definition for R, A, and S are used into equation this, we can write this equation. Area is equal to the cylinder head area plus the piston head top area plus pi bore into stroke divided by 2 R plus 1 minus cos theta minus under square R square minus sine square theta. So in terms of area, we get this equation. Now solving this example. Okay. First we read the statement. This is your example 2-1. A person, John's automobile has a 3 liter. No, it is giving you the total volume of an engine. SI engine, V6 engine that operates on a 4-stroke cycle at 3600 RPM. The compression ratio is 9.5 RC. The length of the connecting rod is R is your 16.6 centimeter and the engine is square. So bore is equal to stroke. Both have the same values. At the speed, combustion ends at 20 degree after TDC. Now, my students, these 3 lines are having a hell of the informations. Let's see what are the informations here. 3 liter. The total volume of the engine has been given to you. So you can find out that this is a 3 liter volume. SI, it's a spark ignition engine. V6 configuration of the engine. So it has a 6-cylinder. Remember this thing. And that operates on a 4-stroke cycle. Okay. So another information. Now N is your 3600 RPM, revolutions per minute. Compression ratio, RC, is 9.5. The length of the connecting rod, R, is 16.6 centimeter. So, engine is square, bore is equal to stroke. Whatsoever we find the value of a bore, we have the same value of the stroke. At this speed, the combustion ends at 20 degree TDC. If you have this cylinder, this is your TDC and this is your BDC. Somewhere here, the 20 degree, your combustion finishes. Okay. So these are the tons of information which is given to you in these 3 lines. Now what we have to do? First, we have to calculate cylinder bore and stroke length. As you know, we have same spins, bore is equal to stroke. The square type of engine is square. The average piston speed, clearance volume VC for one cylinder. Remember this thing. VC for one cylinder, piston speed UP bar at the end of the combustion stroke means of at 20 degree after TDC. Distance, the pistons has traveled from TDC at the end of the combustion. So S at 20 degree. Volume on the combustion chamber at end of the combustion. So volume at 20 degree after BDC. Now let's see. Now for one cylinder, using the equation VD is equal to V total divided by 6 because it's a V6 engine. So number of cylinders are 6. So we have to divide the total volume divided by the number of the cylinders. We have a 3-liter engine divided by 6. So it comes out to be 0.5 liters per cylinder. Now we find out the VD, that is 0.5 liter, or we can write it 0.0005 meter cube. Pi by 4 V square S. No, it's a square engine, so it is pi by 4 V cube. Now we find out that the bore value is 0.0860 meter or 8.60 centimeter. So we know that it's a square engine, so stroke has the same length. Okay, 8.6 centimeter. Now we have find out the first part, the dimension of the bore and the stroke. Now the average piston speed, UP bar. We know the formula, 2 into strokes into revolution. So 2 strokes per revolution. We know the length of a stroke, 0.0860 meter per stroke, and revolutions per minute. We convert it into revolutions per second. So we get the average value of 10.32 meter per second. Now, if you remember, the average piston speed was 5 to 10 meter per second. Now, so we get 10 to 10.32 meter per second, which is in our range 5 to 10, 5 to 15 meters per second. Now, we have found out the bore, we have found out the stroke, we have found out the average piston speed. Now, the finding the clearance volume for a one cylinder. Remember this thing. We don't have to use the total volume. We have to use the volume of a one cylinder because we are now finding for clearance volume for the one cylinder. We know RC is 9.5 and the formula is VD plus VC divided by VC. We know the VD for one cylinder. Okay. Using that values, we find the clearance volume, that is 0.000059 meter cube or 59 centimeter cube. So see this value, clearance volume with respect to this displacement volume. Displacement volume is very much bigger than this your clearance volume, because clearance volume is when your piston is at TDC, only the leftover volume is on the chamber is your clearance volume. So it is very less as compared to your this displacement volume. Now crank offset A is equal to S by 2. So we can find the value of A, that is 4.30 centimeter. Now the ratio of a length of a connecting rod and crank offset, we find the capital value R, that is 3.86 centimeters. Okay. Now to finding the instantaneous piston speed, We know the formula from this equation. Using that equation, we put the value and we find the instantaneous piston speed, that is 6.89 meter per second at the end of the combustion stroke when your theta is 20 degree. Remember this thing. When piston is at 20 degree from TDC, your combustion finishes. At that time, the piston instantaneous piston speed is 6.89, but your average piston speed is 10.32 meter per second. Now, finding the location at what location when your theta is at 20 degree, what is the distance of the piston at which position? Now, using that equation, we get 3, finding the value of S, we find out it is 0.206 meter. So what is the complete stroke length, or 8.60? So at 20 degree, sorry, 0.0860 meter, okay, or 8.60 centimeter. Now, it is at that time, at that distance from TDC. Now, distance from TDC, XRA plus, so at that time it is 0.3 centimeters. So this how we can find different values inside the combustion chamber. Now, finding the instantaneous volume at when theta is you are at 20 degree, finding in non-dimensional form, we find out the volume is this much. And it is, this indicates that during combustion, the volume in the combustion chamber has only increased by a very small amount, and shows that combustion in SI engine occurs almost at constant volume at TDC. When we will study chapter 3, I will explain you in detail volume at combustion at constant volume and terms like this. Okay. Now, the next, first was the engine parameters. Now, with respect in operating characteristics, the second topic is work. The work, we can normally define force into displacement. So the work here can be defined as work is integral of force into displacement. The pistons move. And force, we can also, force is pressure. Pressure is force per unit area. So force, pressure into area, and this P is the pressure in the combustion chamber. AP is the area against which the pressure acts, the piston phase, and X is the distance the piston moves. So we can write this work equation in terms of pressure into area into this derivative of distance. As we know, area into distance is the volume. So area into that distance is your volume. dV is the differential volume displaced by the piston. So we can put these values in equation when the work is equal to integral of pressure into volume, differential of volume. Okay. Now, this is the simplest indicator diagram for a typical 4-stroke cycle SI engine. An indicator diagram plots slender pressure as a function of combustion chamber volume over 720-degree cycles, because one complete cycles takes 360 plus 360. I will explain to you. The diagram is generated on an oscilloscope using a pressure transducer mounted in the combustion chamber and a piston sensor mounted on the pistons or crankshaft. Now on x-axis, we have this volume, and on y-axis, we have this pressure. Now at TDC, your piston is at TDC. This is your piston is moving towards BDC, your intake stroke starts. From this TDC, it is going like here in this, okay, the downward line. Reaches BDC, your intake stroke finishes. SI engine. Now the compression stroke starts. The second stroke, piston is moving from BDC. It is compressing all the intake volume. Then volume is reducing, pressure is increasing, and it's reached the point here. Here, somewhere here, your ignition starts, you get the combustion. It's at constant volume. Remember the term which we have used in the example, just constant volume. Combustion took place. Now the piston is in power stroke. From this TDC, it is going back to BDC. The volume is increasing, the pressure is dropping, and here your power stroke or the expansion stroke finishes at BDC. Volume increased, pressure decreased, you get the power. So now from BDC, the piston is again moving towards TDC. It is above the atmospheric pressure and your volume is decreasing, and it's at the normally constant pressure or the atmospheric pressure, and your exhaust cycle is completing. So this is how your PV diagram, PV indicator PV simple diagram, it's what we will study in detail in chapter 3. Now, because engines are often multi-cylinder, we may have 2-cylinder, 3-cylinder, 4-cylinder, 6-cylinder, or 8 or 12-cylinder. So they are multi-cylinders. It is convenient to analyze engine cycles per unit mass of a gas M within the cylinder. So to do so, volume V is replaced with specific volume V and work is replaced with specific work. So per unit mass of a gas M, so specific work done is equal to work done divided by per unit mass, and specific volume, that volume divided by per unit mass. So we can write our equation. Specific volume is integral of that pressure into derivative of specific volume. Okay, if P represents the pressure inside the cylinder combustion chamber, work inside the combustion chamber is called indicated work. Remember these terminologies, indicated work. So work delivered by the crankshaft is less than the indicated work due to the mechanical friction and parasitic loads of the engine. Work producing inside the combustion chamber is the indicated work, but work which is we are receiving at the crankshaft, that is less than this indicated work, and this indicated work is because we have some mechanical frictions there and we have parasitic loads of the engine. And what is the parasitic loads? Includes the oil pump, the supercharger, the air conditioner compressor, the alternator, and so on. Because they to drive from your crankshaft, so some of that load has to be catered for. So the load or the power or the work which we are receiving at the crankshaft, that is less than the indicated work which is produced inside the combustion chamber. So the actual work available at the crankshaft is called the brake work, WB. Unit of specific work will be kilojoules per kilogram or British thermal unit per pound mass. Okay. Now, 4-stroke cycle of a typical SI engine, I have explained. This is on x-axis, we have a specific volume, and on y-axis, we have a pressure. TDC, BDC, same. You're at this point, piston is at TDC, intake stroke, finish it at BDC. Then it goes to the TDC. Somewhere here, your ignition start, your TDC to the compression stroke finishes, combustion occurs, piston starts moving. This is your power stroke. Here, somewhere here, your exhaust valves opens and you have exhaust blow down. Then piston goes to the BDC, your power stroke finishes, and then piston moves back towards TDC and your exhaust strokes completed. Remember this wide open throttle condition. These are the conditions we will be discussing later on. Now, when you have part open throttle, the graph will be look like this. The curves A section, B section, and C section will be like this. When we are using a SI engine with super or turbocharger, all these curves will be changed. As we have somewhere here below the atmospheric pressure, but here when you have a supercharger or turbocharger, the pressure will be increased. So all these parameters will be above the atmospheric pressure. We will study these things in chapter 3. Now, the brake power, brake work. Brake work is equal to your indicated work minus friction work. WI is your indicated specific work generated inside the combustion chamber, and WF is your specific work lost due to friction and parasitic load. The upper loop of the engine cycle figure consists of the compression and power stroke where output work is generated and is called as gross indicated work area A and C. I am talking about this one, A and C. This is your that area. The upper loop of the engine cycle in figure consists of the compression and power stroke where output work is generated and is called gross indicated work area A and C in figure this. Now the loop which includes the intake and the exhaust stroke is called the pump work and absorb work from engine areas B and C. Net indicated work. Specific net indicated work is equal to specific gross work plus specific pump work, where pump work WP is negative for engine without supercharger. Okay, so W net minus area A minus area B. Engine with supercharger or turbocharger can have intake pressure greater than exhaust pressure, gives the positive work. When this occurs, so we W specific net is equal to area A plus area B. Supercharger increases net indicated work, but due add to the friction work of the engine since they are driven by the crankshaft. Remember this thing. Now, mechanical efficiency, another factor. First, we have discussed the work parameters. Now, the operating characteristics, we have the mechanical efficiency. The ratio of the brake work to the crankshaft to the indicated work in the combustion chamber defines the mechanical efficiency of an engine. Mechanical efficiency of the engine is the specific brake work divided by the specific indicated work or brake work divided by the indicated work. Mechanical efficiency will be on the order of 75% to 95% at high speed for modern automobile engine operating at wide open throttle. It then decreases with decreasing engine speed to zero at idle condition when no work is taken off the crankshaft. I usually give an assignment to my students the term gross and net, or I ask this question, gross weight or net weight. So generally, gross weight includes all the weights of including the material, the packaging, and net weight is the only. Let's take an example of a tube toothpaste. The net weight, which is the material, the paste inside, that is your net weight. And the gross weight is of that material of the paste plus the tube plus the packing, that is your gross weight. So remember gross and net weights. Mean effective pressure is a good parameter to compare engines for design or output because it is independent of the size and engine. First, we have discussed work, then we have discussed mechanical efficiency. Now, the third operating characteristics is the mean effective pressure. Mean effective pressure is a good parameter to compare engine for design or output because it is independent of engine size and or of speed. So mean effective pressure is independent of your engine size, how big or how small the engine is, how how much the speed of the pistons are or the crankshaft revolution. So it is independent of that. If the torque is used for engine comparison, no. If you are using the torque, the larger engine will always look better. If you are using power as a comparison, speed becomes very important. So every factor has its own plus minus. Typical maximum value of brake mean effective pressure for naturally aspirated SI engines are in the range of 850 to 1050 kilopascals or 120 to 150 psi pound per square inches. So for typical value of brake mean effective pressure for naturally aspirated engine lies in this range. For CI engine, typical maximum values are from 700 to 900 kPa, 100 to 130 psi. For naturally aspirated engine, it is 1000 to 1200 kPa, 145 to 175 psi. And for turbocharged engine, for this is for naturally, and for this value is for your turbocharged engine. So with this, we come to the first, no, mean effective pressure. Now, it can be seen from the pressure in the cylinder of an engine continuously changing during the cycle. An average or mean effective pressure is defined by specific work done by. So mean effective pressure is delta specific volume, or mean effective pressure is the specific work done divided by delta specific volume. So work done divided by the displacement volume. Delta V is, you know, that specific volume at BDC minus specific volume at TDC. W is the work for one cycle, specific work for one cycle, and VD is the displacement. Now, various mean effective pressure can be defined by using different work terms in equation. If brake work is used, then we have to use brake mean effective pressure. So the brake mean effective pressure is equal to the brake work, specific brake work divided by delta specific volume. So indicated work gives the indicated mean effective pressure. The indicated mean effective pressure is the specific indicated work divided by delta specific volume. The indicated mean effective pressure can be further divided into gross indicated mean effective pressure and net indicated mean effective pressure. So we use the terms gross and the net, same as the indicated specific work will be used gross and net. And delta V remains the same. One mean effective pressure, so which have a negative value, so PMP, so then specific work, pump work, and the friction mean effective pressure, then we use the term friction mean effective pressure. And we can further correlate these equations with these. Net mean effective pressure is equal to gross mean effective pressure plus pump mean effective pressure. Brake mean effective pressure is equal to net mean effective pressure minus friction mean effective pressure. Brake mean effective pressure is equal to mechanical efficiency into indicated mean effective pressure. Brake mean effective pressure you can also write as indicated mean effective pressure minus friction mean effective pressure as here. So net mean effective pressure and mechanical efficiency of the engine. So this comes to the end, to the first part of our lecture.